Good afternoon, everyone. Hope you had a good weekend. Getting ready to get started here on continuing on 10.4 cross products. And I wanted to take a look at some of the properties of cross products before we finish off this section. We did this for the dot products. I gave you a list of properties. The cross product has properties also. These are in your ebook under the section of Theorem 8. And some of these we talked about, some of these we haven't. So the first property, let me make sure I'm recording, yes. Let's see here. Okay, so the first property here is one that we did talk about. It's that if you take two vectors and cross them, it is not equal, you cannot just flip the order. So you can't, A cross B is not the same as B cross A. It actually gives you a vector that is parallel, it points in the opposite direction, has the same length. So just be careful on that. It's not truly commutative. The second property says if you have a constant times a vector and you want to cross that with a new vector, that you can pull the constant out, cross the vectors, and then multiply by the constant. So just tells you how to treat a scalar multiple. Then this next one is a distributive property of the cross product. So if you have a vector and a vector A and you want to cross it with two vectors that are being added together, you can cross A with B, cross A with C, and then add those two vectors together. So that's distribution of the cross product over addition. And then this is basically the same thing kind of backwards. So you can distribute the C through here. And then this shows you a relationship between the cross product and dot product. This one is a little weird. It's saying if you're going to dot A with the cross product of two vectors, you can cross A and B and then dot it with C. So it's almost like these parentheses can just like move over and switch the operations. And then the last one is just how, what happens when you cross a vector with the cross product of two other vectors. We have this formula. So you don't need to memorize these. You just need to know that these properties exist. And later on, we may need to reference these and say, oh yeah, by property 6, back here with the theorem 8, we can do this, all right? So just be aware that these exist. All right, were there any questions before I continue where we were last time? I had offered that for you to finish off a problem, right? For you to do this one and send that to me as a bonus. Some people did, some people didn't. But let's just remember where we were. We were saying at the end of class last time that if you take two vectors, right, this black one, this red one, and you take their cross product, we know that it gives you a new vector that's orthogonal to both of those vectors. And so we wondered what does the length of that cross product vector correspond to? And it turns out that the length of that vector, the cross product vector, matches up with the area of the parallelogram that is formed by the two vectors. So that's what this picture is showing. Take these two vectors, cross them, take the magnitude, take the length of the cross product, and it gives you that area. So that's where we were. And then I asked you to do that on your own. Or no, sorry, it was this one. Sorry, that one, that problem. I gave you a triangle and you had to find the area. Okay, so a couple more things in this section, then we'll get into 10.5. This is called the triple product. So if you take three vectors this time, okay, take three vectors and you cross two of them, take that answer, right, which is a vector, and dot it with a third vector, and then take the magnitude of that. What you will get is the volume of the parallel piping. That's what they call parallel piping. It's basically the volume of this box. Let me make this box bigger here. There we go. I think that'll work. Okay, so hopefully you can see here we have three vectors. Whoa, I went too far. We have three vectors, right, in three-dimensional space. And if you take this thing called the triple product, which is this computation right here, then what you get is the volume of this parallel piped. All right, I'll give you that volume, which is a pretty cool result. So essentially, if you have like vertices of some box in three-dimensional space, you can find the volume of it just by constructing three vectors and then computing this triple product. All right, so that's just a really nice result of cross products. And then we have an example. So should we do this? I guess we can. So we want to find the volume of the parallel piped formed by those vectors. So I'm giving you vectors, not points, right? So we don't need to convert anything to vectors first. All we want to do to find the volume is take the magnitude of, let's label these vectors. I'm going to call this vector, I've been using, let's say V. I'll call this one U. Why don't we call this one W? So the formula says I do V dot that with U crossed with W. Take the magnitude. Now it does turn out that it does not matter which order you do these. So you could have done U dotted with V cross W, or you could have done W dotted with V crossed with U. You'll still get the same result no matter what. So if I were doing this, I think what I would do is the cross product first. I'd probably do this first. So I'm going to do that on the side here. I'm going to use U cross W. So I'm going to make that little IJK. Then I'm going to put U -2, 5, -1, and then W, which is 1, -1, 1. And then this is where we just kind of play this little game. We're going to get a vector as an answer. And we cover up the I, right? We cover this up. And then we do the little determinant on these four numbers. So I'm going to do 5 times 1, that's 5. Then I take away what I get when I multiply this way, which is +1. And then I move on to the second component of the cross product vector. So this time I cover up the middle, and I do the determinant using these four numbers. So that should give me -2 minus, then here to here is -1. But remember, I have to change the sign, right? Change the sign of that one. And then the last one, I'm going to cover up the K and then do my little determinant here. So we get, let's see, 2 take away 5. And so at the end of the day here, we have what, 4. And then here, this gives us -2 plus 1, that's -1, but then change the sign, so that's 1. And then 2 take away 5 is -3. So there's our cross product of those two vectors. So now coming back up here, V must be the magnitude of the V vector, which is 1, 4, 6, dotted with this thing, which we just found was 4, 1, -3. And the dot product was the easy one, right? You just do multiply here, that's 4. Then add to that these two multiplied here, which is 4. Then add to that these two multiplied, which is -18. And what does this give me here? 8, take away 18, -10. And then we take the absolute value, so we get 10. So the volume of the parallel pipette formed by those three vectors in three-dimensional space is 10. 10 units, whatever the units are, you know, if it were feet, it would be 10 cubic feet. If it were miles, it would be 10 cubic miles. Here we don't have a unit, so we're just going to leave it as a numerical answer. Any questions? Okay. We move on. All right, the last part of this section deals with an application of vectors that I'm sure you'll see if you haven't seen already in physics, and that is how the cross product is used to define what's called torque. So if we tighten a bolt by applying a force to a wrench, then we produce a turning effect. Torque is a vector which represents the tendency of the bolt to turn. So it's some sort of measurement as to the bolt's willingness or I guess rate of turn, not rate of turn, but it's a way of measuring the turning effect of the bolt. And so we've defined it here. T, that's a T here. T, the vector T, is equal to the R vector crossed with the F vector. Now, I need to tell you what each of these are. R is the position vector of the rigid body, which is basically the wrench. So if you have, let me draw it over here. Let's say you're looking at a bolt here. Well, that's not a very good bolt. Looking at the top of the bolt, we have a wrench that comes around this. Okay. Then when we're talking about R is going to be, let me see, I have my picture here. I'll show that in a second. R is going to be a vector that we could imagine is going from the center of the point of rotation out to the edge of the rigid body, which is the wrench. So that would be our R vector. And then our F vector is the force that is acting on the wrench. So we could represent that with another vector, and it could be anywhere. So maybe I'll just attach it, tail to tip, tip to tail here. We'll just call that F. Okay, so here's a vector R, here's a vector F. If we take the cross product of these two vectors, then we get a new vector, which is the torque vector. Okay. Now, because of the way cross products work, we know that if you take R and cross it with F, it's different than crossing F with R, right? It's the same, but they're off by a sign. So your torque vector is actually going to be coming out of the page, either out towards us or into the page. And that's because your cross product is always perpendicular. So I'm about to illustrate this on the next slide, but it says here that the direction of the torque vector is determined by the right-hand rule. Further, the magnitude of the torque is just the magnitude of the cross product of those two vectors, which we know is this. Now, where does that in blue come from? That comes from a formula at the end of last class, that the magnitude of the cross product of two vectors is just the magnitude of the first vector times the second vector times sine of the angle between them. So that's from last class. I never proved that formula to you, but I told you to take it on faith. So let's get to an animation. I think we'll make this hopefully a little bit more clear. So what we have here is a two-dimensional picture. So the black vector is the wrench, okay? So our rotation point is the origin. And then I'm applying a force here. And that force vector is going to result in a three-dimensional vector that's coming out. Oops, it's coming out of the page or into the page. Oops, I need to move this back. Okay. I can't click over there. All right, so just pay attention over here. This over here is a three-dimensional picture of this. So when we take this force vector and cross it with this R vector, the cross product is the blue vector, which is orthogonal to those two. Right? Let me try and zoom out because I want to be able to mess with this, but for some reason I can't. Okay, it's just going to have to work. So let's say we make the R vector a little longer. All right. So now if I take a force and I start applying a force to this wrench in this direction, then I'm going to have some torque, right? And right now, do you see that this torque is pointed up? Now, if I take that force vector and make it smaller, it's still going to be turning, but I have a smaller torque vector, which means you have a smaller torque, right? Smaller force, smaller torque. If I point the force vector in the opposite direction, notice that the torque vector now goes down instead of up. And so that's like kind of the idea of, you're tightening it or loosening the bolt, right? And we follow the right-hand rule. So with the right-hand rule, your right hand, if you take these two vectors let's say we have the R vector here, and the, let's say the F vector is like this. Then right-hand rule says if we translate the F vector over to where they're both tail to tail like this, then when we do torque, right, torque is the R crossed with the F. So if I do this R crossed with F and follow my right-hand rule, my fingers have to point in the direction of R and curl towards F. And so the vector, my thumb should be going into the page. Does that make sense or not? Yes. If I move the force vector to the other side, like up like this, now what happens is over here, we have this scenario. So if I translate that over like this, now if I do R cross F, my fingers are going to point out in this direction and curl towards F like this. So my thumb should be coming out of the page straight at us. And so that's why this vector goes up, as opposed to when it's over here, it goes down. Now I should also point out that that only works if the bolt is a right-hand threaded bolt. Because there is such, you know, we've all probably heard, you know, righty tighty, lefty loosey to tighten something. Well, you can have opposite threads. It could be lefty tighty, righty loosey, but that's usually when do you see that? Has anyone run into something where you're threaded left-handed?
My car tire.
Car tire?
Yeah, the bolts of my tire have left threaded bolts on the left side of the car.
On the lugs? Like the lugs that keep the wheels on?
Yeah, it's really annoying.
Wow. You can, yeah, if you don't know that, you can really mess it up, right? You're trying to loosen it and you're actually tightening it. I know on bicycles, on a bike, a pedal bicycle, the pedals are opposite. So one of them is left-handed and the other one's right-handed. And it's just so that when you're pedaling, you don't accidentally, if something, you know, if the bearings get gummed up or something, you don't accidentally start loosening your pedal until your pedal falls off. It'll always at least tighten it. So anyway, so all of this right-hand rule and torque that goes into the page or out of the page, that whole idea is all based on a right-hand threaded bolt. All right. So there's really nothing there other than to tell you, like, this is about, hey, you know, we've defined the cross product. Now here's a place that you may see it, right? In physics, you may see it when we talk about torque, but it's just all it is a cross product. Mechanically, the mathematics is just a cross product. One more thing I want to talk about before I move into the next section, and that is, remember, I said that when we talk about the dot product, you can take any two vectors and dot them, right? Like, give me two vectors, I can dot them. But when it came to the cross product, what did I tell you about these two vectors? There was a condition. Can we take any two vectors and cross them?
It can't be parallel.
Well, if they're parallel, then when you do the cross product, you'll get zero, the zero vector. So it's okay. It's okay if they're parallel.
Is it you can't do it with two-dimensional vectors?
There you go. Yeah. So we had said you can't do it with two-dimensional vectors. So for example, if I do, let's say I take the vector 1, 3 and try and cross it with the vector, let's say 4, -2, right? Then the problem is when you go to set up ijk to do this, right? You're going to have like 1, 3 and 4, -2. And that's a problem. Because, you know, what do you do over here, right? Further, think about what this is geometrically. If your vectors are in two-dimensional space, let me just draw them. Here's the vector 1, 3. Okay, so that's the vector 1, 3. And the vector 4, 2 is 4, -2 is like over here. Then the cross product should be orthogonal to both of these, right? But you're in two-dimensional space. Your cross product vector would have to be coming out of the page or into the page, but you're in two-dimensional space. So you're not allowed to have an answer that's no longer in the dimension that you're working in. Does that make sense? Therefore, the workaround, the way we can get around this, anytime we want to take the cross product of two vectors in two-dimensional space, is what we do is we extend those into three-dimensional space. So we just throw zeros on to the end for the z component. And now it's this same picture, but we are in three-dimensional space. And so your answer will be in three-dimensional space. It will either be coming out straight towards us or it'll be going directly into the page, right? So it's kind of like the torque, isn't it? Kind of like torque. So I just want you to understand that the cross product in general requires vectors in three-dimensional space. If we see vectors in two-dimensional space, we can still do it, but we have to like expand our space by one dimension. Any questions on that? Okay. All right, so now moving on to the next section. This section's a really important section, and there's a lot of very difficult questions that I can ask you after we get through this section. And your take-home exam, the mini exam, has a few of them in there. So equations of lines and planes. So before I begin this, let's just think about what we should know coming into this class as far as lines and planes. When it comes to lines, here's what you kind of know already. You should, well, hopefully this is what you're thinking. When it comes to lines in college algebra, we had this very nice formula for lines, right? Y equals mx plus b, where m was the slope, right? And b was the y-intercept. So for example, if someone gave me y was equal to 2x plus 1, then it'd be very easy to draw that. I just go up 1, and then slope, rise over run, I go up 2 and over 1, then I just draw a straight line, and then I'm done, right? So lines are something we're familiar with. Vertical lines are a little different, horizontal lines are a little different, but we should be comfortable with lines. And this was kind of like the general formula, the general equation of a line. Now, when it comes to planes, that is a little different because this kind of depends on your background, like who you took and where you took your class. Does anyone know the general equation of a plane? So when we talk about planes, we're talking about like a flat sheet of paper in three-dimensional space, right? So somewhere in three-dimensional space, we have a flat sheet of paper that extends forever in each direction, right? Okay, so anyone know the general equation of a plane? Yeah, so I mean, somewhere it gets lost. I don't know why it gets lost, but do you remember doing this? Do you remember solving systems of equations that were like this? And then something like, I don't know. When you're learning systems of equations, you learn about how to solve, oops, that should have been, I need a Z here, Z, 4Z. When you're solving systems of equations, they tell you about 3 equations, 3 unknowns. Do you remember doing that in algebra? Maybe a long, long time ago. And when they did this, hopefully your instructor told you, hey, look, like actually each one of these equations is a plane. And so what we're looking for is where 3 planes come together. Like where 3 things. So think about, you're all sitting in a room, right? So just look up at the corner of your wall. And if you look, that's where 3 planes come together, right? You have a 2 side walls and a roof. They all come together in a point, don't they? Right? So the solution to this system of equations is the point of intersection of 3 different planes. And if you remember from college algebra, your answer doesn't have to be a point. Sometimes it can be like an infinite number of points. So I'll try and do this way. Let's say that I have 3 planes. Okay, so let me see. Can y'all, let me stop sharing so y'all can see this. Can y'all see me better a little? Okay, so this is plane number 1. I'm just going to put on the ground. okay, here. This is plane number 2, this is plane number 3. So if I put this one, let's say like this, then right now these two planes hit each other in a straight line. And this is so much easier in the classroom. I didn't really think about how hard this would be because we have a lot of things I need to show you how hard this is going to be doing Zoom, but these two hit in a line, right? Like this. I don't know if that shows up. If I bring this plane in, I can also have that plane come in here and hit in that same line like that. And then all three of those planes hit in a line. Do you agree? So the solution to a system of equations does not have to be a single system of 3 equations, 3 unknowns. Doesn't have to be a point like the corner of your room. It could be a line. And then I could take all 3 planes, stack them on one another, and just drop them all down onto the same plane. And now the intersection is the entire plane. So there's an infinite number of points there. Or I could just raise them up, make them all parallel, and then there is no intersection. So you have a lot of different possibilities with planes, but the whole point of me sharing that with you is that, let me get my screen back up here. The whole point of me sharing that with you is that we should know right now coming in that the equation of a plane looks like this: ax plus by plus cz, the way we normally write it, plus d equals 0. Sometimes you'll see it written ax plus by plus cz equals d. That's fine also. The whole point is you have a number in front of x, a number in front of y, a number in front of z, and then some number by itself. And notice also that x, y, and z are all raised to the first power. So if one of these is like x squared, you're no longer looking at a plane. We'll talk about that next class if we get to it. Those are called, well, quadratic surfaces. And so we'll get to that, but right now a plane is going to look like this. Do y'all see that a plane equation is really a line equation without the z? Like if I take this z part out, right? Then I've got some number in front of x, some number in front of y, some number by itself. And that's exactly what this is. Some number in front of x, some number in front of y, and some number by itself. So we're really just adding one more variable on to create the plane. All right, so this is our understanding of lines and planes coming in, okay? We are going to completely like mess up your whole intuition and everything about lines and planes now, all right? We're gonna just totally mess it up. Because what we need to be able to do is draw lines with vectors. So before we can even begin, just want to make sure that we understand what it means to subtract 2 vectors from one another. So if we're given 2 vectors, I'm going to call this R0 and R1. If we compute R1 minus R0, the resultant vector is equivalent to the vector from the tip of R0 to the tip of R1. Okay, what? I'm just draw a picture. So let's say I have a vector, let's call it R0. And then I have another vector R1. But I'm not going to put R1 over here. I'm going to attach it to R0 at their tips. So I'm sorry, yeah, their tips right here. Tip there, tip to there. Okay, I just drew it over here because I want you to understand these can float around anywhere, right? But vectors can be slid around. So there's R0 and there's R1. Now, the main point here is, what does this look like? What does R1 minus R0 look like? So I want to write that a different way. That's the same as R1 plus negative R0. You'll agree with that? Okay, so let me draw negative R0 for you. Isn't that negative R0? Boy, that's a terrible picture. That's a little better. So negative R0 is just R0, but pointed in the opposite direction, right? So now if I'm going to add R1 together with negative R0, I just have to, well, I want to ask somebody. Daisy? Is Daisy here?
Yes, I'm here.
Hey, Daisy. So when you add 2 vectors, how do we do it geometrically, visually?
Is you get the dot product?
Dot product is going to give us something to do with the magnitudes and the angle between them. I'm just saying, if I give you two vectors and I tell you to add them, how do you move them around to add them visually? You attach what to what? Is it not ringing a bell?
No.
Okay, someone want to help?
Tip to tail.
Tip to tail. Which tip to what tail?
It doesn't matter.
Doesn't matter. Okay, it doesn't matter. So what I'm going to do here is I'm going to take R1, okay, which is this vector here. I'm just going to leave it there. And then I'm going to take negative R0, or negative R0, which is this vector here. Okay, this vector right there. And I'm going to attach the tip of that one. I'm sorry, the tail of that one to the tip of this one. So I'm just going to slide this up and put it there, right there. Okay, that's negative R0. Everyone see that? Now, the resulting vector is the vector that would have started here, the beginning of R1, and then go to here. This is what R1 minus R0 looks like. Y'all agree with that? Now, do you see that this vector is really just the vector here? Because remember, vectors can slide around, right? So this is really R1 minus R0. So let me read through this again. Given two vectors, R0, R0, I'll say R0 or R0. R0 and R1, if we compute this new vector, the resultant vector is equivalent to the vector from the tip of R0. So do you see how this vector goes from the tip of R0 to the tip of R1? Okay, just remember that. I need you to understand that before I can show you the next thing. I'll give you one more kind of picture. Okay, if I do this vector u, and I do this vector v, then the vector u minus v should be a vector, who wants to tell me? A vector connecting the tip of what to the tip of what?
U to V.
U to V, right? If I do, wait, hold on. I want u minus v, right? U minus v. So that vector should go from the tip of v
to U.
to the tip of u. Okay, that is what u minus v looks like. Now, if I had done this instead and asked you to do the vector v minus u, then it would go from the tip of u to the tip of v. Make sense? All right, here we go. Now, that was preliminary. Let's now get to, can I erase yet, or you want me to wait for a second? Okay. All right, here we go. So if we're trying to come up with the vector equation of a line in two-dimensional space, so not y equals mx plus b, if we're trying to come up with a new way of drawing lines using vectors, then here's what we could kind of imagine it would be. It would be like, here's a line, right? I've given you just an arbitrary line. I could imagine that I could define this line using vectors by saying, hey, that line is made up of just all the vectors that point to all the points on the line. Does that make sense? So every one of these vectors together makes up the line. It's a new way of looking at lines. Instead of looking at lines as being a bunch of ordered pairs, xy, xy, xy. We look at a line as being just made up of a bunch of points that vectors are pointing to, which means it's really just a collection of vectors. All right. So our challenge is to come up with a way of generating this big infinite list of vectors. That's the challenge. How do we create all these vectors? So here's how we're going to do it. So this is me just saying the vector equation of a line is an equation which generates all the vectors from the origin to every point on the line, infinitely many vectors. Now, we're going to start building up the idea. Okay, so here's the first idea. First part of the idea. Let's say somebody gives us a point on a line, right? Because I didn't ask you this in the beginning, but how many points do you need to define a line? 2 points, right? If you give me 2 points, there's only one line going in between those, right? So the minimum amount of information to uniquely define a line is 2 points. So what about a plane? How many points do you need for a plane?
3.
3, right? If I give you just 2 points, that's not enough for a plane. You need 3 points. Keep that on the side. We'll deal with that later. So let's say we're going to try and come up with a vector equation of a line. Let's say that somebody has given us 1 point. We're going to call it x naught, y naught. Now remember, that's a point, not a vector. Okay, so here's that point right there. That is that point, x naught, y naught. Now, obviously, we can also create a vector that goes from the origin to that point, right? And that vector, we could just call it x naught, y naught. See, using the angle brackets, not the parentheses. So let's call that r naught. It's just the vector that points from the origin to that point. Simple enough so far? All right, next thing we're going to do, I've got to clear this out. So next thing we're going to do is we are going to take a second point. All right, so let's say now somebody gives us a second point. We'll call it x1, y1. We will create a new vector from that called r1. Okay, so we've got 2 vectors right now. We've got r naught, which is x naught, y naught. And we've got r1, which is x1, y1. Now you may be saying, well, wait a minute, hold on. In order to do this, somebody has to give me 2 points. And my answer would be, yeah, of course. If someone wants you to define a line, they're gonna have to give you 2 points no matter what. So it's not like this is too much information. But I'm telling you, that's all we need now. Okay, from this, we should be able to come up with all the infinitely many vectors. Now here's how it's done. So consider the following. What is R1 minus R naught? Now that's that preliminary concept that we just talked about, right? R1 minus R naught should be the vector. And let's ask is it Abimael?
Abi,
What do you want me to call you?
you can go Abi to make it easier.
Abi? So not
Yeah.
Abby, right? It's Abi? Okay.
Yeah, Abi.
That'll be easier for me if I, okay, so Abi. This vector, okay, is actually the vector that goes from where to where?
From the tip of R naught to the tip of R1.
Yep, that's this vector right here, isn't it? It's that one. Now it's actually this vector down here, but we're just going to move it up, right? Good. Okay, everyone clear with that? That is R1 minus R naught. So here's that picture. Here's that vector right there, R1 minus R naught. Now, do you all see, I'm going to call it V, okay? It's the vector V. That's it right there. That's actually R1 minus R naught. Now here's the cool part. Here's the cool part. Do y'all agree that if you look at it this way, R naught plus V, right? If I take R naught and add V to it, you go tip to tail, isn't that just R1, right? Okay. But I could go even further than that. What if I take R naught and don't take V, but take twice V? Won't it give me a point out here? And it'll actually give me a vector that goes from here to here. I'm not drawing the vector, but it would give me that vector, wouldn't it? So R naught, this vector right here in orange is R naught plus 2 V's, gives me that. What if I had 3 V's? So R naught plus 3V would go and have further out, right? 4 V's, 5 V's. So generally speaking, I could do something like this. If I take R naught and I add to it some multiple of V, T, sorry, I'm really exaggerating those arrows on top. Sorry, that's too much. So this is just a scalar, just a number. So if I take R naught and I add a multiple of V, then basically I can create any point on that line by just adding some multiple of V to R naught, right? And I'll just create all of these things. And so this is kind of the general form of a line using vectors, this right here. Now it looks a lot like, it looks like this. Looks a lot like y equals mx plus b, in the sense that it's like a number in front of a variable that's kind of like the m in front of the x. And this is almost like a y-intercept. It's not the same, but I'm just saying it kind of has a little bit of the same format. But I mean, it's not exactly the same. This v, okay, this v that we come up with is called the direction, or the direction vector of the line. So this is now going to be our new master formula for the equation of a line using vectors. R of t is equal to R naught plus some scalar multiple of v, where v is called the direction vector. Very important for you to understand that that direction vector is always parallel to our line, isn't it? That direction vector is always running parallel to our line. No matter what you choose, no matter what number you put in front of it, it's going to be parallel. Okay, so now more language, all right, and notation. So if this is the new master equation we have, where t is a number, v is called the direction of the line, then we can expand this. So we can write this out. I'm going to actually write this out in more general terms. So if we take this, if R naught, remember where R naught came from, right? R naught came from a point that somebody gave us, right? So if we replace R naught in that equation, we'll have X naught, Y naught. And then if we replace the V, right? Or sorry, if we call the vector V the vector A, B. So we're just gonna, we don't know what V is, but we're just gonna say it's some component A and B. Then if we distribute the t through, we get scalar multiplication. So that's t times A and t times B. And then vector addition just says you add up the components. So I'm going to take these two and add them. And then the other two and add. And that's what this is right here. You'll see all this come together in an example. Right now, I'm just giving you a formula, so it might be a little foggy in your mind what the hell we're doing, but it'll all come together. So when you have the vector equation of a line and you're able to break it down like this part right here, this first piece right here, right? And this other one, the part that gives you y, the y component, these are often referred to as the parametric equations of the line. So if you just isolate your attention to the x component, that's called the parametric equation for x. And if you isolate the y component, that's called the parametric equation for y. Further, the a and b in the direction vector are called the direction numbers. And then this last part, I'll show you this in an example. This is a little confusing when I write it out like this. So I think we should just do an example because really that's the way this all comes out the best. I'll go back to the 3-dimensional. So here we go. We have 2 points on a line. First things first, find the vector equation of this line. I'm going to write this on a different page. So I give you 2 points on a line. So I give you a point here, a point here. This one is 3, 6. This one is 7, 14. Okay, so 2 points. Now remember how we did this, right? The first thing we did was that we created a vector R0. So I'm gonna do part A here. R0. So R0 is a vector that corresponds to one of the 2 points we're given. So I get to pick here, whichever point I want. I'm going to pick the point 3, 6 and use that and create a vector. The next thing to do is to figure out the direction of the line, which is V. And V will always be R1 minus R0. In other words, it's just the vector connecting these 2 points. It's the vector that goes from here to here. That's our V. So Lorraine, is Lorraine here? Lorraine. Okay, how about Benjamin? No, Benjamin?
I'm here.
Okay. Oh, there you are, Benjamin. Okay, so Benjamin, what is the vector V for us then? The vector that connects the point 3, 6 to 7, 14.
Yeah. So it should be 4, 8.
4, 8. Everyone clear on that? All right, so to answer part A, it says find the vector equation of this line. We will write R of t equals R0 plus t times V. In other words, R0, which is the vector 3, 6, plus t times V, which is the vector 4, 8. That is the vector equation of the line. So what this means is that if I start plugging in values for t, it will start drawing me the line, right? If I plug in 0 for t, what would I get? If I just plug 0 in here, I get this vector, right? Just out of curiosity, what would happen if I plugged in 1 for t? What would happen if you replaced this with 1 and then added these two together? What would you get?
You get R1.
Yeah, you get this one, right? You get 7, 14. And then, of course, if you replace this with 2, you would be further down the line somewhere. Or if you place it with a -1, you'd be in the other direction. But all the, if you let t be any number, it's going to draw you the whole line. So that answers part A. Part B. Fabiola?
Yes.
Okay, Fabiola. Part B asks us to find another point on the line. So I know right now already that 3, 6 is a point on the line and 7, 14 is a point on the line. But can you find me another point? Tell me how you might do that.
Could you use V or no?
Use the vector equation. This thing right here, you should be able to generate every point on the line with this. So what could you do to that vector equation to give me some other point that we don't already know exists?
We can plug in 1 or 2 for t.
Yeah, just plug in some number for t, right? Now, don't plug in 1 because if we plug in 1, we're going to get 7, 14. So you want to plug in 2, right? Plug in 2. So to answer this question, we just maybe plug in 2 into the vector equation. So that becomes 3, 6 plus 2 times 4, 8. So this is 3, 6 plus 8, 16, which is just, what, 11, I can't do math, 22, which corresponds to a point, that's a vector, but that gives us the point 1122. So the point 1122 should be on the line, right? Good. Adam, how can I get another one? Another point.
You just multiply it by different t, so like 3.
Yeah. Yeah. Could you use negatives if you wanted to?
Yeah.
Yeah. Any number you want. Okay. No, I'm not going to, but that's the idea. We generate the whole line by just letting t vary. Let it be 0. Let it be all the positive numbers. Let it be all the negative numbers, and you'll generate the whole line. Okay. So I think part B we're good with. C. So find the parametric equations. So Terrence, is Terrence there? I see you, Terrence. You able to get to your mic?
Yeah, I'm here.
Okay. So the parametric equations of the line, Terrence, from the notes before, come on. Ah, no, it's on my other, I cleared it out already. Are you okay with the parametric, or are you still a little confused on it?
I didn't quite get the notes down, but
Okay.
I'm pretty sure I got the concept.
Okay. So let me just do this for the whole class. If you're asked for the parametric equation of the line, what you want to do is get it out of this form, which is the form we actually have it in now, and convert it into this form, which means you want to pass the t through the parentheses and then put the vectors together. All right. So we're gonna do that first. So we're going to take our current form. And so I'm doing part C here, this part B, here's part C. What I'm going to do is I'm going to take that vector form and I'm going to pass that t through the parentheses there. So that becomes still a vector, 4t, 8t. And then Terrence, this is where if we were to add these two vectors together, you just add the components, right?
Right.
So what would the new vector be?
So it would be 3 plus 4t.
Yep.
And 6 plus 8t.
Yep. Okay. Now, this is just a very simple thing at this point now. Terrence, this right here, this x component, if we write x equals that, and then this y component, we write y equals this, those are the parametric equations of the line.
Right.
Understand?
Yep.
What a parametric equation does is this. It allows you to easily see what your x and y would turn into if you plugged in numbers for t. Like Fabiola said, let's plug in 2, right? Mm-hmm. So if we plug 2 in right here, we get, let's see, 8, we get 11. If we plug 2 in here, we get 16 and 6, that's 22. Do you see that we can easily pick off the x and y's that way? Instead of having to like plug it in up here and then distribute and collect. It like does it all in one step. We've already done all the algebra. Mm-hmm. Those are called the parametric equations. All right. Okay, good, Terrence. Thank you. The last thing is for us to find the. Oops. I had something paused and I guess it went back to live. Okay. The last thing is the symmetric equations. And these confuse students. And I didn't show you the formula for it. I'm just going to do it. And then you'll see it and hopefully it'll make sense. All right. So the symmetric equations of this line, what you do is you take Terrence's parametric equations and you solve them both for t. Okay, so I'm going to take that equation and solve for t. So I'm going to subtract 3 on both sides. Okay, so subtract 3 on both sides and then divide by 4. And that's what t is. Agreed? Do the same thing on the other equation. Subtract 6. And divide by 8. And you have what t is, right? Now, if this equation is equal to t, and this equation is equal to t, then they're equal to one another, aren't they? So what I can do is set them equal. This, in this form right here, is called the symmetric equations. So this is your, these are your parametric. This is your symmetric. And then this one up here is the vector equation. So when it comes to lines now, we have three different ways we can look at it: in its vector form, in its parametric form, and its symmetric form. And each one of those has its advantages and disadvantages, right? They each have pros and cons. Yes, Jorge?
What does the symmetric equation help us do?
I forgot I was drinking and not breathing. Hold on. I'm okay. I'm alive. I'm okay. All right. So say again.
The parametric equation helps us solve it a lot quicker, but what does the symmetric equation help us do?
Okay. So there's a couple of things with the symmetric equation. Let me ask you this. I talked about V, right? I talked about that vector V. And I said that that vector V, we call it AB, that this is called the direction vector, right? Direction vector. When you look at the vector equation up here, okay, it's very easy to see what the direction vector is, right? It's the vector 4, 8. Here, 4, 8's right there, right? And in this one, do you see where the 4, 8 is? It's the denominators of these. You follow me? Okay, now I'm going to get to answer your question. I'm going to get to answer your question, like, what's the advantage of something like this? Here's kind of a crazy way to look at it. Where was the first problem? I don't think I have it here anymore. Okay, so let's go back to college algebra. Okay, that's your standard equation of a line, right? Okay, so here's what I'm going to do. I'm going to take the 1 to the other side. And then I'm going to get rid of that 4. So I'm going to divide both sides by 4. Now, do y'all see what I just did? What have I created?
Intercept?
Yes. Do these look familiar? Look, could I
Normal
do
line,
this?
isn't it?
Could I do this? Do you agree that this is the same? I need some more room, but do y'all agree that this is the same as y minus 1 over 4 equals x minus nothing over 1? Do y'all agree with that? That's what this is. X is just x take away nothing over 1. Do you see that these have the same form? You see that these have the same form? So the symmetric equation is actually the equation from college algebra. That's what it is. So you can actually take your equation from college algebra, go back to this, and then from here you can actually go back here. Okay? And I mean, but you can tell me right now, if we look at this line, can you tell me what the direction vector is? What's the direction vector?
4, 1.
4, 1. So I know here that V is 4, 1. And this is a stretch, but can anybody tell me what R naught is? So look at this one right here. Can you see R naught in this one? So remember, R naught was 3, 6, right? 3, 6.
Is it going to be 1, 0?
1, 0. R naught would be 1, 0. And so the vector equation of that line would be 1, 0 plus t times 4, 1. So I don't know, Jorge, if this helps you, but what the symmetric is a connection back to college algebra. So we can go back to college algebra from here and then back. We could convert to vector from this. Let's just do a quick experiment. If I were to graph this line using college algebra, I'd go up 1, slope would be up 4 over 1, right? And then I'd connect and I would do that. But according to this one, what I would do is I would start at the vector 1, 0, which is going to be what? 1, 0 is here, right? That's 1, 0, which is out to the right one. And then I add to that the vector 4, 1, which would be 4 out and up 1. That's another vector. And then if I add those together, I should be on this line. It doesn't look like I would be. Oh, you know, I messed up. I see what I did. Sorry. What was the direction vector? This is my fault. What's this direction vector?
1, 4.
1, 4. It's I was looking at this. See how the X has the 4 under it and the Y has the 8? We have to correspond the X and Y's. Yeah, that has to be 1, 4. I'm glad I made that mistake. Then you can see you have to pay attention to the variable on top and bottom. So now this should work. So if we go there to 1, 0, and then go to the vector 1, 4, which is over to the right 1 and up 4, we should add those together and we should be on the line. So anyway, I hope that answers the question of the connection, like why the symmetric is useful. Yeah. Okay. What else? Let's go to the next idea here. So everything we just did in 2-dimensional space extends into 3-dimensional space. So if we have a point in 3-dimensional space, x naught, y naught, z naught, we can create a vector from it, which we call r naught. And if we have a direction vector ABC, not AB, but ABC, then the vector equation of the line is this. It's just r naught plus t times v. Same thing. And then if you distribute the t like Terrence did and collect everything together, you'll have 3 equations now. You'll have one for x, one for y, and one for z. And those will be your parametric equations. Further, if you solve each one of these for t, like we did, then you'll get your symmetric equations, except that you're going to have 3 equations, not 2. Or you're going to have 3 pieces, because you solve all 3 of these for t. So you set all 3 things equal to one another. We'll do an example. This note is just to say, hey, everything we just did in 2D now extends to 3D. And guess what? If we wanted to go to 4D, this would all extend into 4D. We're not going to do 4-dimensional, but everything can extend out easily now. All right. Now, we do need to talk about line segments. Sometimes you don't want to draw the whole line. You just want to draw part of it. Okay, just a piece of it. So if you ever wanted to draw just part of the line, okay, let's say we have a line segment like this. And this point corresponds to the vector r naught. And this point corresponds to the vector r1. If we want to draw just the line segment going from here to there, then I want you to, yeah, I don't like this. I don't like this version. I don't like this at all. Okay, just ignore that. So all we do is use that same direction vector v. We use the same formula. So there's no difference at all in what we're doing. Oops. The only thing that's different is that we will have a restriction on t. We are not going to allow t to be any number. We're only going to allow t to go between 0 and 1. All right, so please ignore this because it just confuses you. So we're going to do an example so you can see this in play. But just think line segment from r naught to r1 is just the same equation restricted between 0 and 1, and it should draw just that segment. And maybe that makes sense with what Fabiola was doing earlier, because I don't know if y'all remember when Fabiola was asked, how can we come with another point on the line? I think initially she said 1 or 2. And I said, well, if it's 1, it's just going to be here at 714. If it's 0, we're going to be here. So this is what happens at t is 0. This is what happens at t is 1. So if we let t be stuck between 0 and 1, we're going to create all the vectors in here, which is going to draw just that line segment. If we let t go past 1, then we're going to be out here, and it's not going to be drawing the line segment anymore. All right, hope that makes sense. All right. Okay, let's see. Hopefully we have a good example here. That one we did. Yeah. All right, so here we go. The points 3, 6, -4, 7, 14, -7 all lie on a line. We are in 3-dimensional space. We've been given 2 points, right? Okay, so first thing I'm gonna do is find the vector equation of this line. So Daniel, you want to tell me what to do here?
We want to find the vector equation. So we're going to, personally, I would start off by titling. I would take my points and I would turn them into vectors and title them.
Okay. So
So
you,
that's kind of a few steps all in one. So I would take the ordered triplet of 3, 6, -4 and turn my R0 into 3, 6, -4.
got it.
And then R1 is going to be 7, 14, -7.
Like it. Yep.
And then this part I might be wrong about. I think it's R1 minus R0.
Yep. So let's call
Okay.
that V. That'll be the direction vector, right?
V is
Okay,
going to be my direction vector. What
is that?
So let's see, I would quickly work this out. This is going to be -4, -8.
Careful. You're going the opposite direction.
I'm going the wrong way.
You
Oh, I am
can
going the
do it.
wrong way.
It'll still draw the same line, but if you're telling me that you're doing R1 minus R0, then it has to be 4.
Yeah, no, I just,
Okay. So 4.
I only can work on a phone right now. My computer just died last night.
Oh, no,
so
it's all right. You're doing great. You're doing great. I just want to make sure everyone's clear on that. That's all.
And -3.
Is it -3? I think so. Yeah. Okay, good. Everyone good with that? So at this point, and good, Daniel, I'll move on to someone
Work.
else.
Do you have to
Um,
flip the, oh, sorry. Do you
no,
flip
no.
the sign of the third one or no?
No, it was -7 take away -4. So it was -7 plus 4, which gave us the -3.
No, I meant the 8.
No, because it's 7 take away 3 that gave us the 4, and then 14 take away 6, which gave us the 8, and then -7 take away the -4.
Oh, I know. I was just wondering when is it then that you flip the sign when you do the cross product?
Oh, cross product. Yeah, that's when we're doing cross product. And it's only on the middle one. Yeah. Okay, so at this point, is Reagan around?
I'm here.
Okay, Reagan. So what would you do now? We're looking for the vector equation of the line. So what would you do at this point?
The vector equation is the one that's R0 plus
Yes.
T times V.
Yes. So let me see here. Put that here for you. So I'm going to write down, it's going to be R of T equals, hey, just so you know this, when I was taking this class, my professor, the way it appeared in our book, they didn't use R, they used U of T equals U0 plus TV. It's basically the same formula as the one we're using, but they used a U instead of R. Do y'all see that? Yes? My professor helped us remember it. He called this the couch potato formula. U plus TV, like you and a TV, right? You're sitting on the couch watching TV. It's the couch potato formula. U plus TV. If that helps you remember it, great. If not, because we're using R, it's not as good, but Vector equation of line is always your initial vector, which is R naught here, plus t times the direction vector. So Reagan, what do we got? Using this formula? No Reagan? Is Reagan gone?
Sorry, I forgot my mic was off.
Oh, no. Okay, go ahead.
It'd be R naught, which is 3, 6, negative 4,
Okay,
plus t times the vector v that we just found, which is 4, 8, negative 3.
yep. And there it is. That's it. Okay, that is the vector equation of this line in three-dimensional space. You go ahead and let v be all the real numbers. It'll draw you the whole line. Okay, so that's part A. Part B, parametrics. So Alberto. Alberto, no. Going once, going twice. Okay, Jared. Is Jared around? Jared going once, going twice. David C. I find it very strange to get 3 in a row. 3 in a row. Okay. Caden.
Here,
All right, Caden. So what are you going to do part B?
so for part B, you'd just do, so you distribute the t and then solve for each of the variables like x, y, and z.
Yeah, just put them together, right? So go ahead and tell me what it is before you solve for each one. Just what is it after you expand it and put it into one big vector? So distribute your fourth or your t through and then join that piece with this piece. So what would you get?
That'll be the direction vector.
Yeah.
Oh, what would you get? Okay, 3
Yeah.
plus x equals 3 plus 4t, y equals 6 plus 8t, and z equals negative 4 minus 3t.
There we go, minus 3t. Okay, does everyone see all we did was distribute the t through and then collect and then added these two vectors together. Now, this is where Caden is saying now this is going to give you your first parametric equation. He gave us the parametric equations already, but I'm just kind of taking steps here. And then this last one is z is negative 4 minus 3t. So those are your parametric equations. There's 3 of them. And then part C is the symmetric. So see, Jorge?
Yes.
Okay, Jorge, how do I get the symmetrics?
Yeah, you solve for t and then set them all equal to each other.
Okay, so what would you get if you solved this one for t? Just kind of tell me what it would be.
X minus 3 over 4.
X
equals
minus
t.
3 over 4. Does everyone agree that's what would happen if you solve that for t? Okay, now we're going to set that equal to this one solved for t. You want to keep going, Jorge?
Yeah.
What is that for t?
Y minus 6 over 8.
Okay, and then that is also equal to this one solved for t, which is
Z plus 4 over negative 3.
negative 3. Good. And again, if you look at the symmetric equations, you can see 4, 8, negative 3. You can see that direction vector again, can't you? 4, 8, negative 3. It's the denominator here, the denominators. All right, part D. We have not asked a question like this yet. So Donald, you're up. Donald, there you are.
Yeah, I'm here.
Okay, so I would like to know, Donald, where this line intersects the YZ plane. So I want you to think about that, okay? Now, I'm going to let you think about it while I'm having everybody think about this. We started out with 2 points, right? Gave you 2 points. We have now come up with the vector equation, parametric equation, symmetric equations for this line. And now the question is, where does this line hit the YZ plane? So is a picture. Oh, that's not the picture I wanted. Graphically, we have three-dimensional space. The YZ plane is, if this is X and this is Y and this is Z, the YZ plane is that plane right there. Does that look okay? It's always hard to draw in three-dimensional space. And then we have a line, right, that's punching through somewhere. It's hitting there. Somewhere, right? And we want to know where. So, Donald, can you tell me anything about this line? And I'm asking Donald right now.
Could you use some of the symmetric equations like x minus 3/4?
Maybe. My thing is, how would you use them if you're going to?
Yeah.
Can you tell me if it punches through the YZ plane, Donald, what's the one thing you could tell me about that point?
Something positive?
Could be. It could be down below. If you're on the YZ plane, that forces one of these numbers to be something.
It'd be 0.
What's 0?
You're
right, but which one of them has to be 0?
I would say y.
Okay.
The y would be 0.
What's that?
The y would be 0, or
all the points on this plane. I wish I could turn this so we could look at it.
Yeah, it's kind of hard. It's kind of hard to like decipher it.
Yeah, but if you're on the YZ plane, that means your y coordinate can be anything. Your z coordinate can be anything.
Which would be the x would be 0.
The x has to be 0, right?
Yeah.
Now, if your x has to be 0, what could you use that might help? If you know here that this has to be 0, looking at your vector equation, your parametric, and your symmetric, which of these three forms is knowing that x is 0 going to allow you to do something?
Ooh.
And I'm going to open this up to Juan also.
Parametric?
I can hear you.
Would it be parametric? X is 0?
X is 0, yes. I didn't hear the first part of what you said.
Oh, the parametric.
The parametric. So yeah, if we look at the parametric, this first equation right here, if I know that x is 0, right, then I can solve for t.
Yeah.
And if I know what t is, then I can put that here and here, and I know what y and z are, right?
Yeah.
So that's the key. You have to make that connection. Once I know x is 0, I can go 0 equals 3 plus 4t. And solving that for t, I get negative 3/4 is t. Right?
Okay. Yeah.
Then I can figure out what y is. Y has to be 6 plus 8 times negative 3/4 because t has to be negative 3/4. And if we plug that into, you get y is, do you get 0 there too? That's just a coincidence. Doesn't have to be 0. So I know what x is, I know what y is, and now I just need to get z. So I'll use that equation. Z must be equal to negative 4 minus 3 times negative 3/4. So I get negative 4 plus 9/4. And I get a common denominator, negative 16. I think it's negative 7/4. Somebody correct me if I'm wrong there. So that's it. We were asked, find where this line intersects the YZ plane. It intersects at the point 0, 0, negative 7/4. Now, it may not seem that we've done a significant amount of work with that, but think about it, right? I mean, we started out with 2 points in three-dimensional space. That's all we started with, right? And now we are able to actually we can tell somebody where that line hits the YZ plane. I mean, starting off the day, that might have seemed like a pretty big task, but as soon as you can come up with the vector equation of the line, And then the parametric and symmetric, you have a lot to work with there. Does anyone have a question as to why we said X was 0 or why we went after this green equation? Is it all clear? Adam, you about to say something? Jorge, I see you. Adam, you're okay? Okay. Jorge, you're good?
We could also use the symmetric equation to figure out the coordinates, correct?
Yeah, we could have used the symmetric. We could have used this. I could have used just those two right there. And I could have replaced X with 0 and solved this for Y. Could have done that. Could have also done this equation and this equation together, let X be 0 and solve for Z. But I think the cleaner way was to let X be 0 here to get T and then just pop it in here, and then we got Y and Z. All right, we're moving on. Determine that these lines are skew. So this is a definition. That is, they do not intersect and are not parallel. So I've given you two lines, L1 and L2. And we want to determine that they're skew. They're in three-dimensional space. So we need to show that they don't hit each other, and we need to show that they're not parallel, and then we need to show that they're not orthogonal. So, okay. Maribel, are you here?
Yeah, I'm here.
How's it going? Okay, can barely hear you, but so Maribel, this question is a little bit tricky, but can you tell me what the direction vector of the first line is? From what we've seen and what we've kind of experienced so far with these lines, can you tell by just looking at this what the direction vector is for this first line?
Yeah, 1, 3, and 1, -1.
1, 3, -1. Perfect. That's exactly right. So everyone, please understand that when you're given the vector equation of a line, the coefficients of the variable part of it give you the direction vector of the line. Perfect. So I'm going to call it V1 because it's the line one, so I don't want to confuse. So V1 is the vector 1, 3, -1. Okay, very good, Maribel. Okay, Iswa, am I saying that right?
Ezwa.
Ezwa, okay,
Yes.
just like it's spelled, okay. Ezwa. How about direction
yes, sir.
vector, direction vector of the second line?
The direction vector of the second line is 2, 1, and 4.
Everyone agree?
I think.
Yes. Now we're using T here for the variable and we're using S here for the variable. It's a different variable. And the reason we're not using T twice is because we don't want to confuse the two equations. We want to somehow differentiate the two from one another. So we just went ahead and stuck with T for the first one, and we're going to use S for the second. Okay, now, as well, very good. Why do you think we went and found the direction vectors to start? Why do you think I wanted us to look at those first?
I think we're trying to find that they don't intersect and they're not parallel or orthogonal. You have to use the vector lines to use in those equations. Like for instance, the orthogonal equation, you have to use the cross product of those.
Okay, you're on the right track. Very good. That's what I was hoping to hear. So the whole idea here, the reason we're looking at the direction vectors is because we already learned that there are easy ways to tell whether or not things are orthogonal or parallel, right? Vectors. And since these are the direction vectors of the line, if these two lines are parallel, right, then the direction vectors should be parallel. If these two lines are orthogonal to one another, then the direction vectors should be orthogonal to one another. So moving on with more people here. I think I've gone through everybody. Well, oh, Lorraine, did I get Lorraine? No. I did call on Lorraine, she wasn't here. Okay, so I got to start over somewhere. So I'm just going to kind of call on people again. Fabiola, you're up again. Easy way to check. Are you here?
Yeah, sorry, I just went to the bathroom. Sorry.
You don't need to talk. You don't need to share that much, but.
Oh
okay.
no, I was just saying because I stopped my video and I just came back. That's why I.
That's okay.
Okay.
You can take breaks, whatever you need. Okay, so I'll come back to you. All right, since you just got here. Adam. All right. Adam.
What are we trying to find out now? If they're parallel or orthogonal?
Yeah, I was going to ask you, what would be an easy way, Adam, to check to see whether or not these two vectors are orthogonal or not?
You find the cross product, and if it's equal to, I think it's 1 or 0, then they're orthogonal.
Okay.
Or no, they're parallel, sorry.
Yeah.
So it would be the dot product then. If the dot product is 0, then they're orthogonal.
Okay, so let's just check that. Let's check for orthogonal real quick. Let's dot the two vectors. V1, dot that with V2. That means take 1, 3, -1, dot that with 2, 1, 4. And if we dot those, we get a number, right? 2 plus 3 plus -4. And that's 5, that's 1, right? We get the number 1. And that is not 0. So they are not orthogonal. Okay, so we've shown they're not orthogonal. Now, parallel. We will move on to Daniel.
Let's see, I gotta remember how to check if they're parallel. We just want to check the direction, right? So
This is orthogonal. So we're looking at
I think, can we use a dot product? Does a -1 dot product tell us that they're parallel?
Unfortunately, no.
Unfortunately,
Yeah,
no.
the dot product is only good for checking for orthogonality. For parallel, you have two choices.
Okay.
Two choices. You have first choice, in which I think is the easiest, is are they scalar multiples of one another? Because that's what it meant to be parallel. The two vectors had to be scalar multiples of one another. The other way is to check the magnitude of the cross product. But I don't feel like doing a cross product. So if you look at this, Daniel, an easy way to check if they're multiples is just ask yourself, what would it take to turn this 1 into a 2? You would have to multiply by what?
2.
2, but does that work the whole way?
No.
No, it doesn't, right? Like I can't multiply this 1 by 2 to become 2 and then that 3 by 2 to become 1. No, it doesn't work. So it's easy. I hope it's easy for everyone to see. There is not a number that I can take, right? I can't just take some constant, multiply it times this vector, and get this vector. That's not possible. Do y'all see that that can't work? It's just a quick inspection. The only way to turn the 1 into a 2 is to make that C be a 2, but then the other numbers don't work. And you could try, maybe you try to turn the -1 into a 4 by multiplying by -4, but then the first one won't work. So, and the second one won't work. So they're not parallel. Is that all right with everyone? Okay, yeah. So not parallel. Okay, now we need to show that they're not parallel. We got that. They're not orthogonal. We need to show they don't intersect each other. This is the harder part. How do we show that they don't hit one another? Well, if they hit one another, right? if they intersect, then there must exist a T and an S such that the following is true. So let's see if this makes sense to you. If these two lines hit each other, then somewhere their x coordinates have to match. Do you agree somewhere? Their x coordinates must be the same. If they're going to hit, if these two lines are going to hit, there's a point that they both have in common, which means there's a place where their x, y, and z's are all the same. So there's got to be some t that I can plug in here and some s that I plug in here where these two will match. Oops. These two will match. These two will match. And these two will match. Agreed? So I'm going to write that down such that 1 plus t must equal 2s, that -2 plus 3t must equal 3 plus s, and 4 minus t must equal -3 plus 4s. So essentially what I'm doing here is I'm setting the components equal. And I'm solving for t and s. So I have a system of equations now. I have 3 equations and I have 2 unknowns, right? 3 equations, 2 unknowns. So I'm going to clean them up a little bit. I'm going to clean these equations up. Let's see, how about this? How about I write -2s plus t equals -1. So all I did here, took the first equation, I moved the s over here and I moved the 1 over here. I'm do the same thing on the next equation. Move the s over and move this -2 to the other side, makes it +2, so that's 5. And then I'm going to bring this one, bring the s over, 4s over, so minus t, and then take the 4 to the other side, so subtract 4, you get -7. So there's our system of 3 equations and 2 unknowns. Any questions on that? So since I only have 2 unknowns and I have 3 equations, what I can do is I can just work with 2 of them at a time. So I'm going to work with these 2, just those 2 first. And I'm going to solve that by doing a quick substitution. So I'm going to take this last equation, I'm going to solve it for t. So all I did there was move the t over to the right, move the 7 over to the left. So do you all agree that that's what t is? You know, and now I'm going to do the second equation, and I'm going to replace the t. So I have 3t. I'm going to replace the t with -4s plus 7, and then equals 5. And this should give me, let's see, distribute that 3 through, so this should give me negative s and -12s, -13s plus 21 equals 5. -13s equals -6, subtracting 21 on both sides. So s is 6 over 13, dividing by -13. What do I do once I know what s is?
Plug that back into the equation where you solve for t.
Yeah, just go back up here and solve that for t. So now I know that t must be equal to -4 times this plus 7. So I'm going to get -24 over 13 plus 7. And what is that? 70, 80, 91. So you've got negative 24 over 13 plus 91 over 13. 70, 67. I think it's 67 over 13. I know I've got some really sharp arithmetic students in here. Is that okay with my arithmetic there?
Yeah.
Okay, so we have what S and T are, right? This is T. All right, so it may appear right now that we have found what S and T need to be where these hit each other, right? But there's a problem. What's the problem? That's the S and T that make those two equal, right? The question is this one true still? Right? So if we take our two answers and plug them into that one, it better work. So if I take that equation, I go -2, let's see, S was 16 over 13 plus T, but T was 67 over 13. Does that equal -1? That's the question. And that's -12 over 13 plus 67 over 13 equal -1. And that is not going to be true. So what that means is that there is no S and T that will make these two lines hit each other. They never have the X, Y, and Z coordinates all the same at the same time, which means they don't intersect.
I have a question.
Yep.
The -13S equals -6. How did that happen, or is that incorrect?
It's probably incorrect. Was this supposed to be -16?
I think probably -16.
Oh man. Shit. Well, that screws everything up. I don't know why I put 6. It should have been 16 here, right? Yeah, right there. Y'all need to like stop me earlier. I think I told y'all maybe early in the semester. Like, I don't know, something about my brain. When I get to arithmetic, my brain just says, nope, been there, done that.
I don't know.
Y'all can do that too once y'all get your degrees and stuff. Y'all are allowed to not care about arithmetic as much. But that's a mistake. So that's going to be a positive 16 over 13. Then you got to change that. But I can tell you right now that whatever we get out here, it's not gonna work. Okay, you'll plug them back in, and they won't work. So my apologies. Thank you for the correction as well. So we have shown they don't intersect. Are y'all happy with that? Or satisfied with the method, the process? Understand? So it takes quite a bit to show that two lines are skew, but it's a nice exercise because you get to do dot product, talk about scalar multiple, solve system of equations. All right, let's see where we are. Planes, yeah, so we are done with lines. This is a good stopping point right here. Are there any questions? Okay, so for the homework assignment for this one, you know, when you go to do your homework in the textbook, you're probably not going to be able to get through everything. So let me just tell you where you should stop. So let's see, lines. So I have you doing 1, 4, 3, 4, 5, 7, 8, or 5, 7. So where do the planes start? So you should be able to go all the way up through 17. Now look, these problems are extremely important out of this section. What I have given you, what we have talked about right now is just the fundamental foundation of vector equations of lines. When you look at your homework, you're going to be like, what the hell? Like, We didn't talk about that in class. And the whole point is you're supposed to try and unravel this, okay? You've got the basic idea now. Can you go unravel these questions? Because they're not as direct forward. They're not just computational like this. You have to really think geometrically, visually, what's happening. So let's see how it goes. I anticipate that you'll have some questions, you know, and hopefully you'll visit me during my office hours or schedule an appointment to meet with me, you know, at a different time. And, you know, just make sure you understand it because this stuff will definitely appear on the midterm. Lines and planes, that's a big topic on the midterm. Okay. All right, we're out of time. Yes.
I have a question. The homework you're talking about is the one for February 1st or February 3rd, since we're ahead?
We're ahead. So I'm saying if you're going to start, like if you've already finished the cross product stuff, which you may not have, if you're going to start working in the lines and planes, only go up through 17. We haven't talked about planes yet. So plane starts at 21. So these problems really, unless you want to get ahead and try it, you can, but I would stop at 17. But I'm also saying that you should be able to handle everything through 17. So even though you may look at it and be like, what? Like you have what you need. You have what you need. It's kind of like what I've done is I've shown you, you know, hey, here's how to use a saw. Here's how to use a screwdriver. Here's how to use a hammer. Now go build that treehouse. Like, I'm not going to tell you how to build a treehouse. You got to figure out how to use those tools to build a treehouse. Make sense?
Yes, sir.
It's fun. It's fun. You'll enjoy it. Okay, everyone, have a good day.
Thank you, sir. You as well.
Thank you.
All right, have a nice day.